So basically we have used, like calibrated curves or backward characteristics to create invariant measures. Invariant measures here under the Euler-Lagrange flow, and also that they minimized the following problem, and this is actually a new minimization problem, right? Earlier we did talk about minimizing with respect to the action functionals, but now, instead of minimizing over all curves, when you let the time goes to infinity and take the average, you turn the problem to minimization over measures. So we would minimize LXV d mu xv. So this is a new problem, and this minimization problem is among all measures that are probability measures, so probability measures on Tn cross Rn, and mu is invariant under the Euler-Lagrange flow. So it's really interesting. It's really a new minimization problem. And as I said, this kind of idea is quite important and relevant in various contexts. And this is a so-called relaxation idea. It occurs not only in weak ham theory, but also in optimal transport. When it's hard to define the transport map, then you would define some kind of joint measures that have marginals, this one and that one, whatever that meant. But then, when you do minimizations over measures, then you have compactness, and that's why it's really important. So that was what we did last time. So I recall quickly here, again, you look at the Euler-Lagrange equation, and this gives you the Euler-Lagrange flow, right? It flows with respect to xt, vt. That's just keeping track with the position and velocity at all times. And a random probability measure is said to be flow invariance if it's invariance under the Euler-Lagrange flow. You take any test function acting on the flow, it's the same. The integral is the same, and this is correct for every bounded continuous function. And last time there was a very good question that the Lagrangian is not bounded, right? It's close to infinity, but you can use the you can cut off and use the monotone conversion theorem, or you can also use the fact that the constructed matter measure, constructed measure is having compact support. Okay, and the theorem we proved last time, that was a big deal. That was, we have a new representation formula. Maybe I put the minus C naught here or whatever. Minus C naught is the infimum, or it in fact the minimum, right? Tn cross Rn L xv d mu xv. And as I said, mu is probability measure and invariant under the Euler-Lagrange flow. Okay, not only that, but also through our construction, we obtained, the inf becomes the means, and we obtain minimizers to the above. Minimizers. Let me quickly recall this idea. This is a very simple but very important ideas in the always in the literature of mathematics when we need to do uh, uh, well, let's say analysis or PDE, is that when you have some sort of process with time goes to infinity, like for example, you have a backward characteristics for s going from minus infinity to 0 and gamma 0 equals to x. What we can do is that we do averaging, right? Again, here, gamma dot in L infinity is bounded. We do averaging and we try to record the dynamics through the averaging behavior. And what I do is that I take for any t greater than 0, I make the measures of the parts occur here. So see, gamma s gamma dot s ds is recorded as a measure c of xv d mu t of xv. Okay, for all c continuous bounded. Again, there's no issue here because our constructed measure have bounded support. And as you guys have observed, for mu t, the support of the measure is only on the part gamma gamma dot, right? But when it goes to infinity, things can change. And then, you know, you have mu t is a probability measure and it has compact support. And here I'm also using the fact that I'm in a Tn, which is a compact manifold without boundary, right? If I'm in Rn, I have to be careful, uh, right? And then you can pass to the limit. Any possible limit is fine. Mu tk converge weakly to mu bar, weakly in the sense of measure. Then last time, what was important that was we showed that mu bar is a minimizer to the above problem. Minimizer to the above problem. And this was originally the idea of John Matter. In 1988 up to 1990 or something. That was the idea. So in honor of that, people call this, all those minimizing measures to be matter measures. Okay. And again, for those of you who have taken or who have seen optimal transport, this idea is pretty much the same when you try to find, the minimizing measures. That's sort of a relaxation idea. So for each of the measure mu that minimize the problem, we call it a matter measure. Of course, again, as I said, here there's something that is a little bit tricky here, what I wrote, that I need to require mu is invariant under the Euler-Lagrange flow. This is quite a restrictive requirement because the Euler-Lagrange flow is, in a way, depending on H, and it's a bit nonlinear, right? Later on, people have ideas to relax this requirement. Okay, but we get to that if I have time. And then now I denote by mu tilde 0 to m tilde 0 to be the support of all possible matter measures, taking the closure. So, so of course, what we define here is that m tilde 0 is a subset in Tn cross Rn, right? Because we are taking both position and velocities into account to be the support. And then for the natural projections that we have often used, then we can define the projected matter measure. So you just project it down to m0. So m0 here is a subset of the torus. So this is a so-called projected matter measure. Matter set, I'm sorry. This is the matter set. you can think it's just the union of all the supports of minimizing measures, and we have defined those minimizing measures to be matter measures. Okay? So those are the definitions, and we're gonna take it easy today. We're gonna prove two results that are quite quick. Well, I mean, in one way they're quite quick, but they're really important. Um, the first result is that remember we talk about backward characteristics and calibrated curves that from any point you can go back, but it's not clear if that point is differentiable. It turns out that for points in the support of the matter measures, so that's the first lemma. If you take point in the support of the matter measures um, here, then you would have that you can run your characteristics or your calibrated curves from minus infinity to infinity. So essentially, if you have xv is in the support of mu of matter measures, then your calibrated curves can go from any time to any time. So any, you know, uh, t to t prime, and this can be taught at just 0 times 0. Okay, so it goes all the way through, and clearly that your function is differentiable at the point at this point in the matter set. Okay, so and then we have certain consequences after that. So in this case, you can say that you have the whole um, uh, calibrated curve in R. Okay, not just array. Or sometimes people can say that it is the whole like it's a whole geodesic line. It's not array. Okay. So let's do the proof. Actually, the proof is simple, right? I mean, we are just using exactly what we have done. Here what I'm writing down is exactly the inequality we have used all over the times, that u minus is dominated by L plus C naught. So this is exactly that. Again, this is just written in this fancy term, right? I mean, this is equivalent to the thing that we have always written down, that u of gamma t prime minus u of gamma t is less than equal to integral from t to t prime L of gamma gamma dot s plus C naught ds. Okay, that's just that. In a fancy term, then we write as a projections of the Lagrangian flow and so on and so forth, but nothing more than that. Nothing new here. Again, what is new now is only that I am starting using something new, that I have my measures, right? So I'm integrating it with respect to my matter measure. When I integrate that with respect to my matter measures, and I realize that the left-hand side, again, because the matter measures invariance, so it's invariance under the Euler-Lagrange flow, right? So as uh, mu is invariant under the Euler-Lagrange flow, clearly that I have, integral on Tn, again, uh, pi is a projection map, so I can just write this one as this one, right? So u minus of pi composed with phi L of t prime xv d mu xv should equals to the integral at any other times, right? Because again, it's invariant, right, under the flow. Right, so that's the key thing that we are using now. That the above part was unknown, And now we are just using the fact that we have new informations about our minimizing measures, and we are integrating that with respect to the minimizing measures. The first part we have at 0. This is not yet using the property of the minimizing measures, but just use the fact that I have its invariance under the flow, right? Um, so that's equals to 0, equals to the second box here. Okay, so those are just using the invariance property. Okay, and now I'm using the above inequality, right? So it's less than equals to integral in time of the action functional integration with respect to the matter measures. And you can see now clearly that we are using the fact that here we are using the fact that the integral in Tn cross Rn of Lxv plus C naught d mu xv equals 0, right? Again, this is because of the fact that it's a minimizing measures, right? If it's a general measure, then I don't have the equality. So this is because of the minimizing measure. Okay, so that's really beautiful. You see that we are always using the two new points, um, naturally in these computations. The first equality was that we are using the the invariance property, and the second one was that we are using the minimizing measure property. So we have 0 equals 0. So we have 0 equals 0. So this means that equality must happen, right? And what does it mean for equality must happen? Equality must happen meaning that on the support of the measure mu, I must have equality, right? I mean, outside it doesn't matter because I'm integrating with respect to the measure mu. So this means that in a clearer terms, equality must happen on the support of the measure mu, right? And in particular, it's clear for us that if we take xv is in the support of the measure mu, we must have equality, right? And yeah, so that exactly meant that I must have that u of the projection map of the phi t prime xv minus, this minus is everywhere because I took the u minus, so I might forget that tl xv. I must have equality. VSL plus C naught ds. Okay, so this is beautiful because it tells me that actually now I have the whole, as I said, I have the whole, calibrated curves, right? Um, Phi 0 Lxv is xv, right? But I don't have just the backward characteristic. I have it. It's for all time, right? So this is phi s L for s negative, and this is phi L for t positive, and it goes all the ways from minus infinity to infinity. So in other words, we have introduced a whole line of geodesic, if we talk about that in the sense of um, distance. And in particular, we have let me just say it, we have a corollary. uh, so we have a corollary that because the 0 is between any time in the between, right? Yes.
Can you just say it again? Why we need to start from XV in support? Where did we use that in the proof?
We use the fact that we must have equality, right? I have 0 equals to 0.
Yeah, but I mean, if we start from any XV, wasn't that still hold.
Yeah, so I mean when I take integration, yeah, maybe I'm so maybe I should have said that it's x naught v naught. So I mean this whole computation, everything from the beginning up to here, I'm putting a box on the left panel. Here is integration with respect to general xv, right? But I'm just saying that once I have this, equality must hold. Maybe let me change this one to x naught v naught. What's happening? Hold on. So x naught v naught is a point here. So it's not related to any xv. This computation is for general xv. But what it says that equality must happen, and equality must happen meaning that on the support of the measure mu, I must have equality, right? And x naught v naught is a point on the support of the measure mu. So then I must have that inside here, um, have the equality. Okay.
I see it.
Yeah, but yes, this computation is for general xv, right? Because when I take the integration with respect to the measure d mu xv, then it for all xv. But clearly that equality must happen exactly on the support of mu.
I see.
Yeah, yeah, but good point. I mean, um actually, so sometimes when I look back into my notes that I just wrote, I'm also confused with myself because like sometimes I need to make it more specific. Um, but exactly that's the point. So the calculation is for general X-ray. Okay. Yeah.
Yes.
So thanks a lot for the question. Um, I think that earlier. So when I was writing this earlier, I was also trying to put x naught v naught, but I was afraid that I put too many of the sub and super indices, and then anyway. Oh, whatever. Okay. All right. So let me get to this corollary very quickly, and then we spend a little bit of time for discussion. Um, what it meant here is that not only I have it can be continue at zero, right? So remember that when we talk about differentiability, that I'm highlighting what is on the left panel now, is a zero is in the between, right? So if any point is in the between, then we have proved that uh, u minus is differentiable at that point, right? So we have a clear corollary that u minus is differentiable at the point x, which is in the support of the matter measure, and we can also compute the gradient, right? So du minus is dv of lxv. Again, v is not a generic v is xv, right? um, so maybe let me write here. So then we have, if xv is in the support of mu, a matter measure, then um, then u minus is differentiable at x, and du minus of x is dvl of xv. And again, this xv is not a general xv, this is the specific point of xv. Okay. And clearly that you have directly right away a corollary that then the set of the matter sets is a subset of this um, C0 level set of H, right? Because of the differentiability property, we have right away that we have H of X dV of LXV equals to C naught, right? So so that is important because it says it tells us that Again, it's contained in the C0 level set of H, and then it implies that uh, this is another concern that you guys asked earlier. So the matter set is compact. Uh, it's compact. Well, I mean, by default, it's closed, right? Because we take the closure, but also that is bounded, so it's compact. That's another important property. And as I said, um, if some of you, some of you here have tried to dealt with the case of unbounded domain. If you replace the torus by Rn or a non-compact manifold, then you lose compactness, and many of the times in the whole literature up to today, 2021, um, that people needed to put the assumption so that the matter set whatever is compact. uh, so that's fine, but it's not very surprising, right? If you put the compactness assumption, then everything goes through. um, if it's not compact, then it's not well studied at all. That's another core direction that one might try to explore. Okay, so let me stop here a little bit for question and discussions. Again, let's take it easy for today, guys. It's end of the night week, and we have done quite a lot. So questions, concerns before I move to prove the last result. uh,
I have a question.
yeah, sure.
So, why is the math measure not unique?
uh why is it not unique? Wow, good point. So uh I have examples to give you later that is not unique. um uh and also that, when we do this minimizing problem, it's kind of like a relaxed version, right? So we don't fix the endpoints or whatever. So we have a lot of degree of freedom, and that gives us that, there's no way to prove that it's unique. Or also that there's the other thing here, that when I constructed the minimizing measures, I'm using weak compactness. I can pass the limit. So in a weak sense, there can be many subsequential limits. Okay, so that's the sort of like a vague answer to your question. Now, in dynamical system, there's a notion of generic properties. So generically, we can we can do it so that the in the generic sense, there's a unique matter measure. So what I meant is that if you I'm not going to go into that in our class, because that's much deeper. Well, not really, but I mean, when I describe the example, I tell you what do I mean generically. But what it meant is that, if you take the Hamiltonian, there can be more than one matter measures. But if you perturb it a little bit, then generically, uh, you have a unique matter measures. Okay, and then this question was the one I addressed last time, was that assume that generically you have a unique matter measures, then can you quantify the rate of conversion of mu t to mu bar? That's totally open. So this whole theory is kind of qualitative theory. There's no quantifying version up to this moment. I mean, in homogenization recently, I mean, with Yifeng Yu and Hiroyo Shimitake, we did have some quantified version, which is interesting. But for this matter measures and for this business, you know, clearly you have measures, right? How do you define the distance between the measures? You can do Wasserstein distance or all kind of distances you wish. And then assuming that you have generically a unique matter measures, can you quantify the conversion rate? It's it's up in the air. Okay, so there are lots of things that is not clear. But yes, I will give you an example. I need to double check and see when and how. I'll give you an example and I'll tell you what's the meaning of generically. And actually, there was a result by Mane, and also there's a result by Patrick Bernard saying that generically you should have only, you know, essentially the set of matter measures very small, and 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 also, yeah, maybe I'm saying too much. I shouldn't bombard you with too many things. So those are enough. Later for later.
Okay, thank you.
But there's already a lot of interesting things that you guys can explore. Yeah, no warranty if it's easy or not. I think they are not easy, but again, that's why it's worth doing research. Like actually, one of my main purpose of choosing to teach this class, it takes a lot of time. Because as I tell you, I know the whole weekend theory from PD viewpoint. That's interesting, but so far I have tried to present to you the weekend theory from you know the schools of fathers or mothers or Mane viewpoint. And um, and the reason is that I try to see from their viewpoints what are not yet done, and I found out that if you want to do any quantitative version of their results, those are not done. That's clearer and clearer to me every day, by teaching this. So, you know, um, if one has a quite good and general idea how to do and understand this thing deeply, it would be great. Other concerns, questions? Okay. Yeah, maybe let me just make a remark, and this is actually our viewpoint. So the problem is exactly maybe a remark. Okay, so generically, um, uh, you can make the matter measure unique. Okay, this is very vague again. Generic notion for PD viewers is always very vague, but I'll give you one example later. Um, and as I said, in this case, multi converge to mu. Uh, what's the rate of conversion is not known. And the third point I want to make is that this is our viewpoint, is that in 1D or 2D, the matter measures and the whole settings are very helpful, because you in 2D you can see that curves are essentially the key objects in understanding the shapes. But our viewpoints, not everyone's, this is our viewpoint in the torus n greater than equals to 3, at least from you know myself or my friend Yi Feng Yu. Our viewpoint is that when the dimensions is of 3 or higher, then the matter sets are too small, uh, too tiny, and sometimes not helpful. Okay, so if you want a good reference for this, you should see the section on uh what I've said and I've forgotten them. uh uh oh man, I'm talking too much. Let me open my book. I suddenly forgot the name. Give me just 1 second, please. Yeah, so there's a section on the headloom example. This is the very famous annals paper in the 40s on the example. This is the example on for Riemannian geometry, but we can essentially, as I said, those are geodesics, right? So we can interpret that as sort of like as matter sets and Hamiltonian dynamics amazingly. And you should see that section if you are curious. So in the torus, in this case, then the headline example tells us that, okay, we in that example, we don't have just one matter measures, we have three, but those are just the three lines. Essentially in R3, you have three lines, let's say not intersecting, three perpendicular lines that are not intersecting each other, and those are all for the matter sets. And these are too tiny, right? I mean, in the whole space, you only have three line segments or lines, and they don't give you enough information about the function u. Why? Because we have proved that u is Lipschitz is differentiable almost everywhere, and it's great here that you see that each of the point on the matter measures give you the whole sort of like calibrated line, the whole line, and u is nice, it's differential on that whole line. However, if you only have just few lines or just one matters measure on the whole plane or on the whole space, then it's too tiny, and we are losing a lot of information because of that. And this is why there's still a lot of unanswered questions in the literature in this aspect. Okay. Okay, great. Um, so now we are ready to prove this very cool result. This is a very deep result. But again, we have come so far that proving this result is very simple. And this answer, I think, like Yoon questions weeks ago, um, was that I have many solutions to the problem, right? I have many solutions to the problem h of x du x equals to c naught. So many solutions. But it turns out that the matter set is a good set. It's a so-called uniqueness set. And this is exactly the theorem. So this is a uniqueness result. It tells us that, okay, you take two different Wickham solution, okay, negative type, whatever. Uh, Again, the problem might have many solutions. I think we come to some more examples soon. But what it tells us is that if the two solutions agree on the matter set, then they are the same. Okay, so you can view the matter set as kind of a boundary set or the uniqueness set. Okay, and yes, in my book there's a PD proof and different ways to do it, but here I'm giving you the dynamical system proof. It's essentially just a consequence of what we have developed so far. That's why it's amazing. Okay, let's just do it. You take any point in the torus and you take C to be a calibrated curve corresponding to U1, right? You have U1 and U2. You can take it to be calibrated curves of any of the two. Let's take it corresponding to U1. So because of it's corresponding to U1, you have equality, right? So it's kind of a minimizers or a calibrated curves for U1. So you have equality for U1. And for any other use, including U2, you don't have equality, but you have inequality, right? So that's that. Okay. And clearly that the idea is simple. Now you're just going to compare the two, and then you take the last time average and pass the limit. When you take the last time average, you pass the limit, you get to matter measures. That's all. That's the whole idea. Okay. So go along calibrated curves, take last time average and pass the limit. Okay. So Yeah, so from the above, we infer that I can compare u2 minus u1 is less than equals to u2 ct minus u1 ct. And then now you are taking the average, right? So u2 minus u1, because the right hand side is correct for any t, so I'm gonna take the average. So this is the average, right? And for the average, you write as now as a measure, right? The average in TK being written as a measure. This can be seen directly from here to here, and projection, forget about that. Okay, and pass the limit, you get to two matter measures, right? And because u2 equals to u1 on the matter set, so they are, they are the same on any matter measures, right? So the integral of that is equal to 0. So we are done. Okay, so it's beautiful. Yeah, so this is another main principle that we often use, is that, again, we go along calibrated curves, and then we compare the values, and then we take the lifetime average. When you take the lifetime averages, then you get two matter measures. Okay, and again, there's no need to emphasize why lifetime average for PD and dynamics are important. And at this moment, in various different kinds of PDE, like also like for dispersive PD, understanding the lifetime limit is very, very hard and challenging. So, once you have obtained the result for lifetime average, then you can use it in this kind of simple procedure to deduce certain results. And this is a very deep result. I mean, like, to get to this result, well, at least we lost 27 lectures. Well, not lost, but we we spent 27 lectures to get to this result. So it's by no means easy. But yeah, it's cool. Yeah, so I think I'm done with the lecture today. I'm taking it easy today. We have time for questions.
I have another question. So is that proof that saying that math measures are only like one dimensional? How's of dimension?
Uh, no. So good point. So generically, there's a conjecture of Mane. It's still not done. It's only done in two dimensions, and that's a result. Like Figali published it in Inventionist. That generically, you should have that. The matter measures, or even the Aubrey set, which is a little bit bigger than the matter measure, should be just a point or a periodic orbit. So if it's the case, then it's only one dimension. But uh, yeah, so that's a big conjecture. Uh,
I
but
see.
generically, it's very like for a PD person, like for a PD person, you're given a Hamiltonian, you have to deal with that. But for people in dynamics, here what they meant by generically is that you're given a Hamiltonian. So this is for for us, we have to deal with that, right? Okay, you can do approximation and stuff like that, but you are given something and you have to deal with that. Uh, but then for what's the notion of gener generically? in dynamics is that you're gonna perturb it by a potential energy. So you're gonna plus some c of x, and c here is kind of like also not in the measure sense. C is sort of like let's say dense, So for a dense set of c in the space of c infinity of the torus, generically we should have the matter measure, uh, h plus c x has a unique matter measure mu, and the support of mu should be is just a point or a periodic orbit. Periodic orbits, and it's clearly one dimension, right? You go and you finish at a given point. Essentially, I can say that this is known in 2D. As I said, 2D is quite special. You can use the geometry in 2D. In 2D, there's no way for curves to bypass each other, right? They have to, there's a whole rigidity in 2D, but not in 3D or higher. Uh, but also that this generic notion is very important and very beautiful in dynamics, but sometimes it's not useful for PDE, right? Because if you plug in a function C, then the problem becomes different. Uh, yeah. So yes, there's a trade-off, and so far I have been more on the PD side, and yeah, but who knows, right? Yeah, yeah. But any other concerns or question?
I, can you see more examples of maldersive or uniqueness sets?
More examples? Okay, so I'll give you one example. I think that I will try to devote one lecture for just some simple examples.
All
But
right.
yeah, I can tell you that in advance that in general, there's no clear example. So yes, you can. I'm not gonna do also the headline example, but go and check it. That should be easy for you guys to read. The headline example in by the end of my book, chapter 8 or something. Let me check. Um, yes, chapter 8. And also there's a general version of that recently, and that's pretty much all we can say. The problem with dynamics and this kind of areas also that we don't really have good and clear examples. I will give you very simple examples. It's related to the Icono equation as well. So it's related to the Icono equations related to classical mechanics. That's the easiest example I can give. And there's also another example for the so-called magnetic Hamiltonian. But other than that, I don't have any examples. Uh, for a good reference, you can check some papers on um, um, some further references you can read. There's a paper by um, Alessio Figali and maybe Ludovic Refort. Again, there's a paper on Manet conjecture if you want. Manet conjecture. Um, it's quite good. I mean, you guys should be able to understand some parts of it based upon what we have done. And there's also a paper or series of some papers by Patrick Bernard. This is exactly on the numbers of ergodic matter measures. I mean, ergodic here means that actually I'm reading one at this moment. I'm reading the very short paper by, let's see, what's the paper by, uh, by so there's a paper by Patrick Bernard and Contreras. Uh, this is just 10 pages in the annals in 2008. Um, and it says that also generically you can show that the set of ergodic matter measures is finite. So essentially, again, if you have two matter measures, you can take a linear combinations. It's a convex combination. It should still be a matter measures. So what it says is that generically the set of matter measure is finite dimensional. It's a convex set. So ergodic matter measures are the measures on the exposed points of that set. And they say that the numbers of ergodic matter measures finite generically. Um, it's just 10 pages. I have I've been lazy. I've never read it, so I'm reading it now. uh, yeah. Okay.
Thank you.
Yeah. So a lot of great references. You guys should read it. And okay, maybe I'm throwing too much at you, but you know, again, my point is that you all are fresh and new and having amazing ideas, maybe sometimes naive, but I have a great belief that naive ideas pretty much are better than sort of like routine ideas. That's my belief, Okay, great. Again, thanks a lot, and we are done with night weeks so far. And yeah, I'm grateful that we have not had any glitches in terms of internet connections or stuff like that. Hopefully, there's none as time goes. And have a great weekend. Again, stay safe and healthy. Um, vaccinations are available, but still being careful. I mean, I don't know. All right. So see you later next week. Bye for now. Thank you.